Good morning. Let us resume our discussion. So what were we discussing in the last class? Any quick recap?
We were discussing about SIFT and edge elimination using Hessian matrix. Then we moved on to shape-based descriptor, which was basically HOG, and we learned how to form it. And then we ended up conclusion with nearest neighbor matching.
Right. So we were discussing about scale invariant feature transform. So we have seen how to detect the key points in scale invariant feature transform, which are robust or stable across scales, and also how to eliminate the key points which are not very easy to match or distinguishable from the neighborhood, such as edge points, outlier points, or weak key points, and so on. Okay, and then we also have seen how to localize them better. That is, we can see how through Taylor series expansions, sub-pixel level accurately localization is possible in scale invariant feature transform. And then subsequently, we have seen how to assign orientation to these key points and also use the reference orientation to represent all the key points and match irrespective of the rotation of the object. And we are in the process of looking at how the matches are established in scale invariant feature transform features through scale invariant feature transform features. Okay, so I will just quickly go through some of the slides. This is very good opportunity to ask if you are not clear on any aspects of the scale invariant feature transform. Okay, so this is the probably last class on scale invariant feature transform, and we'll be moving on using this feature in a higher and better applications. Okay, in the subsequent lectures. So on feature extraction, as such, this will be one of the last class, especially on scale invariant feature transform. Okay, so we have seen these steps, and then we have also seen how to create the scale space. To extract features at different scales, we convolve with different sigma Laplacian of Gaussians or different variance-based Gaussians, and then find the difference of Gaussians there. Okay, so we have seen how scale space is created and the number of images, okay, in number of scales in an octave, how they are decided, and then the number of octaves also, how are they decided, that we have discussed very briefly in the last class. So here is a picturization of that. So how they these are slides from Professor Mubarak Shah. So as I mentioned, so for many of these things they have used empirical studies. It is conventional even in computer vision even now to use empirical studies for setting up the hyperparameters or the parameters which are not very mathematically can be found. There are some fields like mathematics and again statistical signal processing and signal processing, where you can have actually purely analytical methods to fix some of these parameters or to determine the values of parameters or estimate the parameters or estimate the signal itself and so on. But computer vision is a mix of both. It does has the methods which are driven through optimization, driven through purely signal processing front, and also driven through some of the empirical studies to deal with the real situations. Okay, when things go towards more and more realistic, there is no hard and fast rule to set some of these things or to find out some of these things. So what they have done here is they have applied. So since for each key point, we have now each key point is associated with a, x, y, okay, and sigma and orientation, difference orientation as well. Okay, so these are the four things now they characterize a key point. So if whatever the key point we have, any key point can be characterized by all these four things. At which scale it is found, with what reference angle do we represent that key point, or what is the dominant angle corresponding to the HOG of that key point, and then at what location it is. Okay, so given all that, we would like to see how if I see across two different images, okay, will that same key point, will it match at the same scale or not? Okay, or will it match at the same scale and orientation or not? Okay, so such things also we can see. And then further, if I see across two images, and if I find out some key points here, some key points there, can I see actually, so 1, 2, 3 are key points here again, so whatever, A, B, C are key points here. So if I keep matching, how many key points do I match? Corresponding points I match accurately. In the sense that if 1 is corresponding to A, and 3 is corresponding to B, and 2 is corresponding to C, when I try to match, just taking the key points without knowing the other details, okay, will I be able to match them very accurately? Say what will happen? Identifying key points is easier, or the matching is easier. Which do you think is easier? Say if I ask you a question, so I have two tasks. Okay, I have given two images. First task is identify the key points at, say they're all key points are at same scale. Okay, assume that. I just want to see whether the key points here and key points here are identified or not. That is the first task. Second task is, after identifying the key points at the corresponding scales and locations, can I match them uniquely or not? Okay, that means the key points here and corresponding key points there, can I match them uniquely or not? Which is a difficult task, or which will have a more error?
Finding the key point.
Okay, finding the key point itself is a difficult task.
Yes, sir, because it involves a lot of steps.
Okay, but how do I match the key points? So doesn't it need initially to find the key points? See,
yes, sir.
If I find the
okay,
key
so
points,
matching includes finding key points as well.
What is that? Can you repeat?
So, sir, you mean to say that matching itself includes key point extraction?
Right.
Matching.
That's
so
true.
It's a bigger
What
process.
I'm saying is, say for example, here I know that, so x1, y1 and sigma 1. Okay, this is one key point. This, say I know that a priori that here are the key points, and then x2, y2 and sigma 2. Okay, this is the second key point. Okay, and so on. I know up to x5, okay, y5, okay, and sigma 5. These are the key points in the first image. I know that. Okay, so I put first image, okay, 1, 1 here, okay, on the top, just to indicate it's a first image. I also know that in the second image also there are 4 key points. Okay, so x1, 2, okay, x2, sorry, x1, y1, sigma 1 again, here all 2. Okay, and then x2, y2 and sigma 2. Okay, the second key point, and so on, x4, y4 and sigma 4. I know initially the ground truth locations where the key points are exactly. Okay, and then I also know, because I have synthetically I may generate an image. Okay, I know where exactly the key points are. I also know at what scale, if I convert with a Gaussian, the key point will come up. So I, based on the key point, the extent of the blob that I'm supposed to get, I can decide on the scale as well. Assume that I have this knowledge a priori. Okay, in 2 images. And also I know that these 4 key points, first 4 key points are corresponding. Okay, 5th key point is just not corresponding point. Okay, there is no corresponding point in the second image. Now the first task is, can I get the identify the key points in image 1 and image 2 correctly or not? So among 9 key points I have, how many key points do I identify at their appropriate scales, appropriate locations? Okay, out of 9, what is the score I get? Okay, that's the in terms of key point identification. This is the first task. Second task is, after identifying these 9 key points, task 1. Okay, second task is, after identifying the key points, what I would like to do is, I would like to match this 4 to 4. Okay, 4 in first image to 4 in second image. So there are how many combinations possible? So 4 to 4. So how many combinations possible? 16 combinations, assume that it is possible, or for 4C2 combinations possible. Roughly assume that 16 combinations possible. Among these 16 combinations, only how many are correct combinations? Only 4 are correct combinations. Okay. So now the question is, can I pick out of these 4 combinations correctly or not? That is the second question. So which task is more difficult? Say if there is an error in task 1 itself, do you think that I will be able to perform task 2 correctly?
No, sir.
Yes or no? If there is
No,
an
sir.
task 1, can we perform task 2 correctly?
No, sir. We won't be able to.
We will not be able to do. So now, which task is more like, which task will have more error then?
Matching will have.
Yeah, matching is obviously prone to more error. The reason being, the first task itself, if I am not able to do properly, that will creep in the subsequent error in the second task, because second task depends upon the first task. So here what they have shown is, here matching location and scale is the error here, I can see. So this is the error. This is repeatability percentage. Okay, and then the number of samples per octave. And this is the, I think this is the error, if I am correct, or accuracy. This is the accuracy, since it has gone up to 100%. So the accuracy in the first task is matching to the scale, and so I am just denoting like this. Okay, matching to the scale and location is this. So if they match with this much of accuracy, then at corresponding, say what is the accuracy which they can match is this. Okay, it will be lower than that. Hope you people understand that, right? So you can see that if I am able to match at a, say, number of scales per octave is what is given here. So if I consider 4 scales per octave, and this is the repeatability, that means I do it 2 times, 3 times, etc. Because what happens is, because of numerical aspects, okay, so it may not exactly give the same location, okay, in terms of identifying the key point. And also this, they keep rotating the object, and then same object, but it is at different variations, okay, in different images. Now the same key point I want to locate in across these images when it appears in a different ways. Okay, so that's in some sense characterizes the repeatability. So if I see for 4 octaves, like number of 4 scales per octave, okay, that means if I take 4 different sigmas per octave, and with that I measure the difference of Gaussians, then what we see is the accuracy with which I can match to the location and scale the same key points is, say, you can see that say 90%, close to 90% or 88%. Okay, I just put some number, 88%. And the accuracy with which we can match the corresponding points, not just identifying key points, but matching across images, is 81% or 82%. Okay, so that's the difference. I hope you understand these curves now. So similarly, what they have done is, they have done for identifying different parameters, hyperparameters in their method. The second one is, with what sigma we have to start. So what is sigma naught? Okay, that is the question. Again, for that, what we do, we see actually we generate different images which are known with known location of their key points and then scale. Okay, and we would like to see where they are, whether they are correctly detected or not, first identified or not. So you can see that the key points identified are all here. Okay, for prior sigma of 1.2, 1.4 and so on. And then the ability to match is here. Okay, across different images. Here also you can see that the accuracy with which we can do with the different sigmas varies. Here also you can see that with the different scales per octave varies, and based on that they want to select one the number of scales per octave. How do they select? See, wherever the it is peak, that means the accuracy is higher, that you can select. Okay, accuracy is higher both in terms of identifying the key points, also in terms of matching the key points. Okay, so you can select ideally this one, but if you want to be a little more stable, you can also select 4. Okay, so they have selected, I think, 4 scales per octave. Okay, so if you increase the number of scales per octave, there is no improvement in the accuracy. Okay, so it's no need. So this work they have conducted, or this experiment they have conducted with, I think, thousands of key points, several thousand key points. Okay, and then here the prior value of sigma they have taken to be 1.28. There is not much improvement with respect to the value of sigma. I think 1.2 is what they have taken, or 1.6. Yeah, probably 1.6 is what they have taken. So, and then this is, I hope it is clear. How do you find the peak in the scale space? As you can see here, the 27 pixels I am telling is around this pixel 3 cross 3, around this pixel, just a scale below that scale, again 3.3 cross 3, a scale above that scale. That is, this is sigma naught, and this is sigma 1, and this is sigma 2. If you wish to find a key point, if you wish to find whether this is a key point or not, what we take is 3 cross 3 region around that key point. Okay, in the Gaussian convolved image at a scale higher, at a 1 scale higher, 3.3 cross 3 and 3 cross 3 region in a scale that is just lower than the current scale. Okay, and then you take all this 3 cross 3 cross 3, okay, region, and then see if this center pixel is the highest pixel, maxima among all this, or maxima or minima, that is extrema. Once you find the key points, then what do? We denote the key point. Okay, if this is the key point we have identified, we denote the key point with the scale, location, and the orientation of the key point. How do we denote? So XY anyway, where the location is very, very clearly seen. The length of the key arrow here is proportional to the scale at which it is identified. If the length is very small, it means that it is identified at a smaller scale. So it is identified at a smaller scale. This length is big, means it is identified at a bigger scale. This might have identified at a sigma equal to, say, 1.6, for example. This might be identified with sigma equal to 1.6 into 4 or something. Okay, something like that. Hope you people understand. There are different ways of representing how the key points are, where the key points are. One way of representing is through arrows. Other way of representing is through circles. Okay, so they represent through ellipsoids as well. So they represent through ellipsoids like this. Okay, in some other representation. In some other representation, they do represent with respect to the rectangles. Though represent the key point, if this is the key point, they may represent like this. Okay, and then if this is the key point somewhere, okay, they may represent like this. Okay, so there are different representations for the key points. This is through arrows is one kind of representation. If you see conventional computer vision papers, you will see all this. Okay, so key point representation, if they have applied any of the key point identification and then feature extraction strategies, there are several strategies that are developed. Okay, on the top of scale invariant feature transform. And they all show the key points like this. So the orientation is also shown by the arrow here. Okay, and even the circles, ellipses, all those also show the orientation. Okay, in which the key point is detected. Now you can see that if we directly detect the key points, there are several key points that are detected. So probably if close to 800 key points are detected, assume that. Then what they wish to do is they would like to localize it and then eliminate the weak key points. Okay, and through that they could reduce from 800 close to 800 key points to close to 700 key points. So this reduces the number of key points. This only retains the strong key points. Okay, and the threshold used is this much. After that, as we discussed, they consider the principal curvature or the Hessian matrix. Okay, second derivative corresponds to the curvature. Okay, and hence the Hessian matrix captures the curvature. That means how well it deviates. The key points deviate from a straight line. Is what is being, or the derivative of the intensity pattern deviates from a straight line. So that is being captured by this Hessian, and that is being shown here. And we have seen, as we have seen, this is the measure they use instead of R measure that is used in Harris corner detector. And if R is greater than 10, it is not a key point. Okay, if R is less than 10, okay, it implies it is a key point. Key point corresponding to what? Corresponding to corner. If R is greater than 10, then it is key point corresponding to what? If R is greater than 10, then the key point is corresponding to an edge. Okay, so then they further eliminate the key points and reach to the very robust key points. And then as we discussed, they perform the orientation assignment based on the magnitude and orientation of the gradients. Okay, so they compute both magnitude and orientation of the gradients here. And then they take the, they perform smoothing with a Gaussian. Okay, and then take the gradient magnitude. So like we do in Harris corner detector, here also they use a weighing function while computing the HOZ or the histogram of orientation gradients vector. The smoothing function used is a Gaussian function. Okay, with this scale, with this sigma. Once they assign orientations, they will get the dominant orientations. Okay, they get the all HOZ vector for the at that location. So if at a given x, y, comma, sigma, okay, now they will get a HOZ vector. So if we consider 8 bins, okay, as is seen here, they will get an 8x1 vector. Okay, 8x1 vector indicates the magnitude weighted angles. Okay, as we discussed before. And if the values are say 10, 50, okay, and 35 and so on, 100 or whatever, if these are the angles, then there will be one dominant direction in which the key point is oriented. That is considered as reference direction. Okay. And what they do is they perform a little bit of few other operations on this. They do normalize this to get a better assessment in matching. So if we see how many key points are matched across location and scale, and then how many key points are matched across location, scale, and orientation, corresponding orientation. That means if I know the rotation to be 20 degrees, my key point orientation is also identified as 20 degrees, then it is correctly detected. Like it is correctly detected with respect to the location, scale, and orientation. Okay, like that. So matching with respect to the ground truth, how well we are able to identify a key point with respect to the location and scale is shown here. Okay, in the top, the first one, and this is the second one, second curve. Okay, and then this is the third curve. Okay, so matching to the orientation, scale, and location is more difficult than just matching to the scale and location. The reason being there may be some false orientation assignments when we go from location and scale to the orientation. And then matching the corresponding points or identifying the corresponding points is even more difficult, because only if all the key points are detected to the scale, orientation, and location, then only the matching or the in terms of the corresponding points establishing through nearest neighbor will be simpler or accurate. So this is how they are. So they analyze with respect to the image noise, and they also analyze with respect to the view variations. Okay, it is in fact during that time, this is the best demonstration in terms of identifying the key points, matching across the key points, matching across the objects in the images, and so on. In fact, this is the very celebrated method of computer vision for that era. And it's patented and it's widely used in many computer vision tasks. So as we discussed, what they do is once they get the HOZ vector, so they have given some steps on exactly details on how exactly they are constructing the HOZ vector. That is 8 bin, okay, for each 4x4 region, and concatenate the if we have actually different key points, they will concatenate and get the big vector describing the object. So you can see the exact details, how they have got 128 dimensional key point. They also identified how many, like HOG also, how many bins to consider, and then how much region to consider around the key point. All those things are investigated. The another important thing to note is they normalize the key point before the normalize the HOG vector before matching. This is very important. The reason being, finally HOG vector what you get will be 8x1. And as we have seen in the previous examples, this ranges from, it's a real number. Okay, 80, 20, and so on. Okay, 100. Okay, and then it can be 120 or whatever, 200 or whatever. Okay, it can even 500, any value can come. Now, if you would like to match, that it is better to have a common range. So for that, what they do is they first normalize this. Normalizing means they divide by the square root of all this, norm of this vector. Okay, v by norm of v. Once they perform it, what will happen? Each of these elements will range maximum from 0 to 1, correct? And then 0.01, 0.1, okay, 0.15, okay, 0.002, and 0.5, and so on. If there is any value that is, and then sum to 1, these also sum to 1, okay, they will be like that. Each element is less than 1 and they sum to 1 because we are normalizing the norm of the vector. Now, if we see that one element is very high, that is 0.5 or so, it means that this may be due to noise and may not be really the dominant orientation. So in such case, what they do is they remove that as outlier to make a better or consistent match or a stable match. So what they do is, if the value is maximum is say greater than 0.5 or 0.2 here, they will bound by 0.2. That means this is this is written in such, this is clipped such that the maximum value is 0.2. And then again renormalize to have the some of these elements to be 1. Okay. So this is how they perform the, this is the how they construct the feature vector, feature descriptor. And with this, they perform nearest neighbor matching. To remove the ambiguous matches, as I said, so they take the first best distance, D1. Okay, the second best distance, D2. If this ratio is 0.8, greater than 0.8, it means that they are very close. Okay, and hence it is an ambiguous match. So they take all these precautions or all these measures to get really very good matches. And as you can see here, the ambiguous matches they have identified, they explained, saying that this can match with this and this and this with a very close distance. In such case, we need to take care of it, or we have to remove that as a potential match. See, for most of the computer vision tasks, if I want to identify a an object same in both images, how many matches do you think I need? Say, how many corresponding points do you need? I think we need to get. This is an object, assume that it is somewhere, this is the same object. Okay, what I need to get is this object 1 and object 1 has to be a match, and then there is an object 2. Okay, and then object 2 has to be a match. Okay, so how many matching points do you think we need to establish the match or the identify the same object in 2 different images? How many do you think? Do I need 1? Just if I get 1 corresponding point, is it enough? Or do I need to get 10 corresponding points to uniquely match? Or do I need hundreds of corresponding points? Say, assume that I just need to identify, is it a same object or not? Okay, I got some key points here. I also got some key points here. How many matches do I need? Can anyone answer this? Okay, I will rephrase the question in case if it is not very clear. Assume that we have a single object now. Okay, and this single object is say I just want to check whether it is this may be there in this another image as well with some rotation. Okay, or some shear or whatever. Now what I'm doing is I'm just identifying the key points. I have identified key points here. Okay, and I can identify any number of key points, assume that. Okay, how many number of key points are required to say that if there is a rotation alone? Okay, how many number of key points are required to say that image 1 and image 2 are just same, just except for a rotation? How many key points are required to establish that image 1, okay, x comma y is equal to image 2 x dash comma y dash, where x dash comma y dash is related to x comma y through a rotation matrix? How many matches are required, or how many corresponding points are required?
More than 2.
More than 2. Very good. So if I get more than 2, it is good enough to match. And minimum, how many are required? Minimum
2.
2. Okay, right, good. So I need not have, even if I have 2 very reliable key points, it is good enough. If I have 50 points which are not very reliable, do you think will I get a better match or better identification of the rotation matrix compared to having 2 potential key points, corresponding points, which are very accurate in terms of their correspondence between the 2 images? Which is better, having 2 accurate corresponding points, or having 50 roughly accurate or non-accurate key points matching between the image 1 and image 2? Which one do you think?
Accurate 2 points.
Yeah, accurately having 2 points is good enough. So in the same manner, to match across objects as well, okay, across images to match the objects as well, it is good enough to get a minimum number of or reasonable number of key points with highly accurate correspondence, rather than having more and more number of key points, okay, or corresponding points. So for that reason, removing these ambiguous matches also gives us a very good improvement in terms of matching, as they have shown here. So if you see the ratio of above 0.8, then the accuracy goes, that means this is the accuracy in matching incorrect matches. Okay, this is the accuracy in incorrect matches, and then this is the correct matches. Okay, so above 0.8, if D1 by D2 ratio is there, then the correct matches will decrease and the wrong matches will increase. So they have put actually some 0.8 or so for the threshold. And with all these things, the proposed method by David Lowe is scale invariant feature transform that is widely used, as I mentioned. So any questions on this? Okay, so if you people have no question, what I will do is I will indicate how these kind of feature points are very effectively used in matching in large scale, in image retrieval, in object detection, and few other tasks. So there are several other methods in line or after subsequently with scale invariant feature transform that are proposed in computer vision. So I will name a few. Scale invariant feature transform is the method in 2004, as I mentioned. So after that, the very fast implementation of scale invariant feature transform is being proposed. That is SIRF. Okay, and then after SIRF, also there are several methods which use different kind of key points. So rather than using the key points with Laplacian of Gaussian, maxima in Laplacian of Gaussian space, convolved images, can we have the key points extracted slightly different ways? Can we extract the key points through a little bit of better optimizations? All those things are explored. And one of the method which uses these key points of extraction and feature description very well in computer vision is bag of visual words. What this does is, say if I need to match a particular image, okay, and if the problem can be classifying an image into one of the classes, let's take the simple classification problem. And then this is also useful, as I mentioned later, for many other computer vision tasks. We will discuss that as well. So what it does is say, it says a class 1 of images. Assume that you have actually images of class 1, class 2, and class 3. These are different classes of images. The elegance of this bag of visual words is it can be used in both supervised and unsupervised setting. It can also be used in as a better feature extractor, in sense that even compared to the scale invariant feature transform or any key point based features, it does give better representation of the whole object in terms of features. See what scale invariant feature transform does. It identifies different key points, okay, and then gives a feature vector around each key point, but there is no unified connection or the connected set of features. Okay, so what we are doing is each key point will have a HOG vector. Okay, and this also will have a HOG vector, but the whole description as such is not coming up. Hope you got the point. Say if I want to identify a car, each corner of a car is a different feature. Where is the integrated information coming up? Okay, that is not very well seen in scale invariant feature transform based features. Similarly, car versus a person, versus a cat, okay, versus a dog or any other objects. Okay, if you would like to match or classify or detect, what we do is each key point act as a one piece of information. But where is the collected pieces of information representing the object? That information is not coming up. This bag of visual words gives a representation of the object. That means if we have the features at different local regions or different parts of the object, can I make a collected decision or collected representation of the object with putting together all these features? Can I benefit from that? That is being appraised by bag of visual words. Okay, so this is in fact this has come up from the natural language processing kind of framework, which is already there as bag of words, okay, in that community, and that is being applied here with bag of visual words. This also takes the feature vectors by scale invariant feature transform or any other transform where it gives the local features. So it takes all different local features and then integrates local features for classification, for detection, with a holistic representation of the object. So I will discuss some of these details of this, then you will get a better picture of what I am discussing. Also, this is again another important advancement in computer vision. So hope you got the point I have mentioned. So if I give you a bicycle, for example, so you know only that actually there is a handle and then there are some wheels and so on. Okay, but you don't know the connection between them. Okay, so there is a handle here and so on. Okay, but you don't know the connection between them. Okay, so that connection can be established in the bag of visual words. Okay, so assume that there are different classes of images. So let this be this class of images. Let this be just to have a very different viewpoint or easy perception. Let this be medical images. Okay, let it be just X-rays or some X-ray images and so on. Let these be persons images. Okay, and let these be instruments. Okay, musical instruments. Just to have a complete different picture. Now, what the idea of bag of visual words is, see, if you see the key points here in medical images, you may get some key points. If you get in the persons or the humans, okay, you will get different kind of key points. Okay. And if you see in musical instruments, you may get a different kind of key points. Okay, different kind of key points. Now, the nature of key points, if you see in this class versus in other class, they will be different. Is it not? That means a human key points, if you see, you can see eyes, okay, you can see hands, you can see legs, okay, and so on, and head. Okay, these are all eyes, hands, okay, legs. Okay, if you see medical images, you may see different bones. Okay, and then there may be some other structures and so on. Okay, so if you see in terms of musical instruments, okay, there may be some strings. Okay, some wooden keys or whatever. Okay, different kind of features. So if you see, each is a word, okay, or a visual word. The kind of visual words we get in different classes of images are different. So as I mentioned, this has roots from the bag of words. What it conveys is, if we consider a set of documents, okay, this is one set of documents, document class 1, okay, and then class 2 documents, and then class 3 documents. In class 2 document, if we consider these are medical documents again, and these are business documents, and these are, say, corresponding to science or technology documents. Okay, then what happens? All medical documents will have the words which are more frequently occurring will be different from the words that more frequently occur in business documents. The words that more frequently occur in science and technology documents are even different. So if I get a dictionary of more frequent words here, here, and here as code words or whatever, okay, then I use only these words as the clue for me to classify a test document. I will be able to do it quite efficiently. That is the idea here. So if I see medical documents, what is the kind of words I may get? Okay, so health, and I may also get about say doctor, say exercise, and few others. Okay, here if I see business documents, okay, what will frequently occur? Money, and then stock market, and few others. Okay, lending. Okay, if I see science and technology, okay, education, okay, or whatever, development, okay, or whatever. So yeah, innovation, etc. So what if I see among several documents, if I count the frequency of words here, what I measure is the frequency of words. Then if I see more frequently occurring words, I assume that I organize them, I arrange them in more frequently occurring words. This may be occurring for, say, out of say 100 documents, this may be occurring for 1000 times. This may be occurring for 900 times, this may be occurring for 700 times, and so on. Okay. Similarly, if in business documents, okay, money may occur for say 10,000 times, Okay, and then this may occur for 800 or 8,000 times. Okay, and this may occur for few other. Okay, 500 times or whatever. Okay, so like that. So here also you can consider. So these are considered bag of words. What we are representing? We are representing a class by a bag of words. Okay, and now if I have a test document, okay, what I do is, say now I construct a whole bag with all these words together. So assume that I have 10 words here. I have again 10 words here, just to give easy picture. I am taking same number of words, but not necessary. Assume that here only 8 words, which are very frequent. Okay, I just take only very frequent words. So total 28 words here. I see the frequency of this, okay, test document, okay, to all these 28 words. Then what will happen if it has more frequency for the initial words, then it can say that these are all these, say 1 to 10 words, or another, say 20 words here. Okay, and then 28 words. So initial words are all corresponding to the medical. Okay, and then this has a small frequency here. And this will have this assume that this has a very small frequency. Then what does it indicate? The document, test document, belongs to medical document. Okay, so this is the idea of bag of words. Any question here? Okay, we can also, what we can do is, we can see in the documents, we can construct the, based on the frequency, there's a feature vector. Okay, so if I have a training set of samples here, for all training set of samples, 100 samples, if I know which are the highly occurring words, for each of these 100 documents, I will measure, okay, how much is the frequency of these words in that document 1, okay, to document 100. And each acts as a feature vector. For a test document, I will also construct a feature vector and then find out the distance with respect to the training samples of this feature vector of this class, and this class. That is the other way of doing. Okay, so the basic picture is, we find out we want to identify the bag of words which are more frequently occurring in different classes. Okay, and then put together, and then we would like to see the test document is close to what kind of documents, or what kind of words are more frequently occurring in test document. So same thing here, if we consider now, instead of words there, we have key points here. Okay, and each key point is like a word, and description of word is through the key point descriptor. That means you have a HOG vector here, right? So this HOG vector of 8x1 will help us as a descriptor for this key point. Similarly, if I have key points for all different class of images, okay, I have the key points as the different words. Okay, now given all these words, what I try to do, what I first do is, for this class, I will perform the most frequently occurring words. Okay, for this class, most frequently occurring words means here what? Most frequently occurring kind of key points, which are the patches that are quite well seen in that class of images. In human images, what are the patches that will be well seen? Eyes, nose, and kind of things are very well seen. There may be different representation for eyes, okay, in different persons, but they are very well seen. Okay, among the eyes, they all closely match compared to eyes to nose, or eyes to string, or eyes to wooden keys, and so on. Okay, so like that. So what we do is, we apply a kind of grouping of the several key points and the key point descriptors we have in each class. With that grouping, that is referred to as clustering, we can get the visual words. What is these visual words? Visual words are the representation of that class. So let it be only, so you have actually some very frequently occurring words here. And then similarly for each of the classes we will get that. And then what we try to do for a test sample also, we get the key points and then try to see how well these key points will match, okay, to which of the visual words. Okay, so if they match quite well to the class 1 visual words, then we can say that the test sample belongs to class 1. And if they match well with the test sample 2, they belongs to class 2, they belongs to class 2 and so on. Any questions on this? I will show anyway pictorial depiction of this in the next class. Okay, but if you have any basic questions, you can ask today now. Okay, no questions on this? Okay, I will ask a question before I close. So where are we using scale invariant feature transform description here? How is scale invariant feature transform useful in bag of visual words? Can one of you answer?
The identification of the key points. This
Right.
words.
Key identification of key points is one. Where else? After identification of key point, are we not using anywhere scale invariant feature transform? Yeah, can complete a menu.
So matching also like we do.
Yeah, matching also we do, but we don't need to match here. Description we have to do. Key point, say what we mean by identifying key point is only locating where it is. Okay, where the key points are in an image, because the remaining image will be uniform or maybe not very interesting, like high information regions. Okay, region of interest may not be there in other regions. So we identifying the key point location is one thing, and describing it by the
Descriptors, HOG.
Yeah, HOG descriptor, which is also with respect to TA orientation and normalization and so on, is other thing. So the HOG descriptor as used in this is referred to as SIFT descriptor. Okay, just to SIFT descriptor is slightly different from HOG descriptor in the sense that it is with respect to take reference orientation and also with normalization, we are representing HOG. Okay, so that's where we use this shift. After shift, what the next step is a kind of clustering or grouping, because what we get is if we take hundreds of images, we get to say 10 power 6 key points, okay, or even more, very large number of key points. We don't want to use all of them. We want to cluster and see the representatives of that class, representative key points of that class. That forms the visual words. Okay, with put together forms the bag of visual words. And from there we try to establish the, so we construct now a new histogram. This new histogram is on, say for visual word 1 to visual word 100. What is the frequency with which in a given document or in a given image, what is the frequency of these visual words? So if V1 to V2 are more frequent, it means that it may belongs to class 1. V2 to V3, if they are more frequent, it may belongs to class 2 and so on. Okay, that we know a priori because we know which visual words have come from which class. I hope this is clear. Hopefully in the next class, we will discuss with the slides as well, and it will be much more clear. So if you have any questions, you can anyway ask now. Otherwise, we will conclude the class for today. Thank you then.